Section 1.6 is all about solving other types of equations and other types of functions. Our first type of equation we're going to deal with is a polynomial equation. So a polynomial equation is the result of setting two polynomials equal to each other, usually the number 0 or other constant number. An equation is considered to be in standard form if one side is 0 of the polynomial and the other is in decreasing powers of the variable. So starting with the largest exponent and getting smaller as you go. The degree of the polynomial equation is the same as the highest degree of any term in the equation. So you have a degree and a leading coefficient. Some polynomials of equations 3 or higher can be solved by moving all terms to one side, thereby obtaining 0 on the other side. Once an equation is in the standard form, we're going to factor if possible, or we will factor, and then set each factor equal to 0. So if we're looking at this first example here, we're going to first set this equal to 0. So we would take the 3x to the 4th power minus 27x squared, and now it would be equal to 0. And we ask ourselves, what do these terms have in common? Well, they're both divisible by 3 and by x squared. So we just factor out that GCF. 3 divided by 3 is 1, x to the 4th divided by x squared is x squared. 27 divided by 3 is 9, and x squareds would cancel out. Now you're not just done here though, because hopefully you recognize this is still a quadratic term, and we can factor it one more time. In fact, we can factor this as the difference of two squares, where the square root of 9 is 3, so it's x minus 3, x plus 3. Once it's in factored form, it looks like the quadratics we had last class, and so all we're going to do is set each of the little pieces equal to 0 and solve the equation. So we would have x, 0 divided by 3 is 0, the square root of 0 is still 0, add 3 to both sides, and subtract 3 to both sides. And I forgot my minus sign. Oop, there it is. Okay, so here are your 3 solutions for this degree 4 polynomial. This is a repeated root, so there are 4 solutions. Let's try another one. Now this one is interesting. Because there are 4 terms, we're going to have to use a process called grouping. Grouping is used when there are 4 terms in your polynomial. We have 4 terms here because if we set this equal to 0, we end up with x cubed plus x squared minus 4x minus 4 equal to 0. There are 4 terms. 1, 2, 3, 4. Now what I want to do is I want to separate these two into the first 2 terms and the second 2 terms. And we're going to take the GCF of each term separately. This is the grouping mechanism. So if we look at the GCF of the first 2 terms, well, they're both divisible by x squared. So x cubed divided by x squared is x, and x squared divided by x is 1. The blue terms, both of them are divisible by negative 4. If we divide that away, negative 4x divided by negative 4 is x, and negative 4 divided by negative 4 is positive 1. So we've taken the GCF of both terms. Do you notice now that there is a new binomial GCF in both of these terms? They both have the binomial x plus 1 attached to them. Well, that means that's the new GCF for those 2 terms, the x squared term and the minus 4 term. So we can take the GCF out, and I'm left with x squared minus 4. I notice again that I have the difference of 2 squares. I can factor. And once everything is as completely factored as possible, you'll use the zero product property to take each individual piece, set it equal to 0, and solve. So this is x equal to negative 1. This is x equal to 2, and x equal to negative 2. There are my zeros, or my solution to this equation. Again, this grouping mechanism happens when there are 4 terms in your standard form. We had 4 terms. First 2 have a GCF, second 2 have a GCF. You should get the same binomial here, in which case take that out again and write your leftovers down. Factor as much as possible and continue to solve like last class. The second type of equation that we're going to solve in class today is a radical equation. A radical equation is an equation in which a variable occurs in a square root, in a cube root, or any higher root, like fourth or fifth root. Here are the steps. If necessary, arrange the terms so that one radical is isolated on one side of the equation. Raise both sides of the equation to the nth power, usually second power, to undo a square root. Solve the resulting equation, and if it still contains radicals, repeat again. Now it's very, very, very important that you actually do this extra step right here, step 4, of checking, because radical equations can have extraneous solutions or roots, so we do actually have to check our work on these problems or else you're bound to get one wrong, kind of like the rational functions from 1.2. Now I've solved this first one for you so you don't have to write it down like Speed Racer, but I do want to write down what's happening here. If we look at where we started, this square root was not isolated. So I had to subtract 2 from both sides so that the square root is by itself on that side. So let's make a note to ourselves that we isolated the square root here. The next step I did is I'm going to square both sides. Since I'm squaring both sides, I actually have to square this. This is a perfect square trinomial, so if you know the shortcut, you can take it. Otherwise, you need to double distribute or FOIL, so multiply. However you know how to multiply, with the shortcut or with FOIL. We'll just go ahead and put FOIL down for ourselves, assuming that's the way most of us will take. Now that all of my grouping symbols are gone, you're going to set the equation equal to 0. I always recommend going towards your x squared term, meaning you're going to move these pieces onto this side. Because your x squared term is already positive, that just makes it easier. You assess what kind of equation you have left. If you still have a radical in your equation, you're going to have to do all this process again. But right here, we only have a quadratic. So once we're down to having a quadratic, all we have to do is factor, and we have to solve. However, if you stop here, you are done. Because remember, we have to check and see if one of these solutions would be extraneous. So what we're going to do is we're going to set up our original equation right here. And anywhere there was an x, we're going to put our solutions in and see if we are correct. So we go to our calculator and we ask, hey calculator, is 2 times 5 minus 1 plus 2 equal to 5? That's plugging an x everywhere there was, plugging a 5 everywhere there was an x a second ago. The correct answer here is yes. 2 times 5 is 10. 10 minus 1 is 9. Square root of 9 is 3. 3 plus 2 is 5. So we're good to go. We can put a box around this guy. He's good. But if we go check this one, 2 times 1 minus 1, quantity plus 2, is that equal to 1? Again, these are the two places where the x was in the equation. 2 times 1 is 2. 2 minus 1 is 1. Square root of 1 is 1. Plus 2 is 3, and 3 is not equal to 1. Therefore, this is an extraneous solution, and we'd have to throw it away. Let's see an example live. Now, I'm going to go through this example a little bit quick. Obviously, you can slow down this YouTube video and or pause and catch up as I go. But what we're going to do first is we're going to isolate one of the 2 radicals that we have in this problem. Mathematician's choice, but I'm going to keep things positive, which means I'm going to isolate the square root of 3x plus 1 by adding the square root of x plus 4 to the other side. Now, I'm going to square both sides to get rid of this square root, which means what I'm going to do is I'm going to square this term, 1 plus square root of x plus 4. Now, I'm just going to write it twice so that you can see the foiling distribution, because I'm assuming more of us will want that method. Okay, so let's go ahead and FOIL this. 1 times 1 is 1. 1 times square root x plus 4 is square root x plus 4. Plus 1 more of those. Plus square root x plus 4 times square root x plus 4. That means that we are just going to have x plus 4. Now these parentheses are unnecessary, but I just wanted you to see that they're grouped together. I would not actually write them though, because there's nothing to distribute. If we notice, we have a whole bunch of like terms that we can start to combine. we can move the 1, the x, and the 4 all to the left side of the equation and combine together both of our square root of x plus 4's on the right side. The 1's are going to cancel. We end up with 2x minus 4 equal to 2 times x plus 4. My radical, again, did not eliminate out of this problem. So unlike question example 4, where we would just have a cute little quadratic to solve, we still need to deal with this other radical. So I'm going to follow the same steps again, which said isolate the radical. We're going to do that by dividing by 2 on both sides to get rid of the 2 in front of the radical. And now I'm going to square both sides. To maybe write this in a way that makes more sense to you, we're going to take this and we're just going to write it twice so we can actually see that foiling happening. This becomes x squared minus 2x plus 4. My recommendation is that you always go towards the x squared term, which means we're going to move everything to the left side of the equation this time. This is going to be x squared minus 4x plus 4 minus x minus 4 equal to 0. Continuing to condense this and combine like terms, this is negative 5x plus 0. Ooh, plus 0, don't really need that, so we can get rid of that. Those 4's would cancel, and we're left with equals 0. Now we have a cute little quadratic, and we go back to the skills we had from last class. This is 2 terms, which means I look for a GCF. They do have a GCF of x, so I can factor that out. And now I can use the zero product property to find my 2 solutions. Now, before I put a box around these confidently, we do want to check our work. I'm going to let you pause right now. I want you to take these 2 proposed solutions of 0 and 5. I'm going to want you to plug them into the original equation. Not to give it away, but one of them we're going to have to throw away. Hopefully you paused the video and you did actually try to plug these in, and you'll notice that we had to get rid of the 0 because when we checked our work, it was not true. 3 times 0 plus 1 is 1, square root of 1 is 1. 0 plus 4 is 4, square root of 4 is 2, so that would be 1 minus 2, which is negative 1, not 1, so it's gone, it's out of there. Again, these steps are listed above. We isolate the square root, square, condense. Isolate the square root, square, condense, factor, and solve. So it follows now that if we can solve square root equations or radical equations, we can also solve equations with rational exponents, since rational exponents can be rewritten as radicals. So we have the steps here to solve radical equations that are in rational exponent form. So we're going to assume that the powers used here, the fraction used in the power is in simplest term, and they're all positive, okay? We're going to isolate the expression with the rational exponent. We're going to raise both sides of the equation to the reciprocal power. Notice that this is flipped over. Let's write down the word reciprocal. That reciprocal power. If m, which is your new denominator power, is even, you need that plus or minus symbol. If m is odd, you do not need the plus or minus symbol. The odd index only has 1 root. Again, make sure that you check all of your proposed solutions to ensure that they work, and then we should be good to go. You see, I've done the first one for you again, where we're isolating first the term with the powers, which means we were isolating this guy. We had to add 6 to both sides, and then divide by 3 to isolate the term with the fraction power. After that, we raise both sides to the reciprocal power. Notice the reciprocal power is 4 over 3. It essentially cancels out the 3 over 4 power, so that just becomes x. But now we have 2 raised to the 4/3 power. The top number of your fraction goes inside the square root, not square root, sorry, the root. The bottom goes out and becomes the index. So this is the 3rd root of 2 to the 4th power. Now at this point, again, I will be asking for both exact answers and for decimal approximations. This is an exact answer because I'm going to pull out a trio of 2's from the 4 2's that are in here, wow, and it goes to the front with 1 left over. Then I can type that in my equation. Let's see what this looks like, okay? Hang on with me while we try one. So very first, what we want to do is isolate the term with the exponent. So we want to get that by itself. This one's a little easier because all we're going to do is add 3/4 to the other side. So this is going to be x to the 2/3 equal to -1/2 plus 3/4. Now, for us to be able to add fractions together, they need to have a common denominator. So if I change this denominator to 4, it's like I multiplied it by 2, which means I change the numerator to 2. That means this becomes x to the 2/3 equal to 1/4. Now I'm immediately going to raise both sides to the reciprocal power. The reciprocal power here will be 3/2. Since that denominator, that reciprocal power here, has a denominator that's even, we have to remember to put plus and minus in front of this problem. We didn't need to do that in this question because my denominator of the reciprocal power was odd. Now all we need to do is find an exact and a decimal approximation answer. So let's remember what this means. So we're going to keep that plus and minus floating down, but there's a rule with these guys that you can toss the exponent to both the top and the denominator. Okay, let's do this a little bit by little bit. Let's go to the top. What is 1 to the 3rd power? Still 1. And then square root 2, because top goes in, bottom goes out. Top goes in, bottom goes out. We're really just getting the number 1 on the top here. This one's telling me to bring out pairs of numbers. So the pair of numbers I have here is I will have a pair of 4's and a leftover 4. Well, the square root of 4 is 2, so this is like saying 1/4 times 2, which is plus or minus 1/8. Now that's our exact answer, and we can always turn that into a decimal for a decimal approximation. Again, one more walkthrough with these is you are isolating the term with the exponent. You are raising the power to the reciprocal power, and then basically simplifying from there. The next type of equation that we're going to work on are very interesting. They're called equations that are quadratic in form, not quadratic formula, quadratic in form. This is a quadratic or an equation that can be expressed as a quadratic equation using appropriate substitution. We call this U substitution. Equations that are quadratic in form contain an expression to a power, that same expression to a power squared, and a constant term, aka they contain an expression, a constant, let's use number 5, and that same expression squared. So that looks like a quadratic. This U, however, might be something kind of crazy. By solving this U substitution quadratic, we'll be able to find a simpler quadratic to factor. So for example, do you recognize that if this was x squared minus 8x minus 9, this would be a regular quadratic. However, it's like we took an x squared and squared it, and took an x squared right here. So it really is quadratic in form, it's just not actually a quadratic. So what we're going to do in these kinds of problems is we're going to write the following. We're going to literally write the word let u equal to x squared. Where did I get this x squared from? Great question, right here. So then I can substitute with u substitution. Everywhere there was an x squared, I put a u, which means this turns into u squared minus 8u minus 9 equal to 0. Well, I can guess and check factor this very easily. this is going to be a u in the front and a u in the front. The numbers that multiply to 9 and add to -8 are 1 and 9, where this would be negative and this would be positive. Now, we're done u substituting because we did do our factoring, So we're going to undo u substitution and put back what we substituted before. So now I'm putting back, everywhere there's a u, I'm putting back the x squared. And we assess, can I factor any more? This first factor, that's as good as it gets. But this one is the difference of two squares. So we can keep going. This is x squared plus 1 dropped down, x minus 3, x plus 3. We solve each of these, we'd say x squared plus 1 equal to 0, x minus 3 equal to 0, and x plus 3 equal to 0. This first one is interesting because when we take the square root of both sides here, we just get the square root of -1. So that means that we have two solutions at positive and at -I. The other two are pretty easy to solve. We're just going to use the opposite sign here, which means this is 3 and this one is -3. So we have our four solutions for this quadratic form quartic function. Now, not all equations that are quadratic in form are quartic. In fact, they can be kind of crazy, like the two examples you're going to see on the next page. But the bottom line is we're u substituting, meaning we're taking a pause, we're saying, hold on. This is very confusing when it's written like this, so let me make it simpler. This I've been factoring all day. Then we put it back. So I've done one of the examples here for you just so you can see a crazy example. Remember, I have my u substitution where we're going to let u be equal to x to the 1/3 power. Where'd I get that from? Right here. So all of this right here is my u substitution, where any of the x to the 1/3 power change to u's. It's way easier to guess and check factoring this, 10, 1, 11, when it is u's instead of x to the 1/3. Of course, I've got to put it back. So here's me putting it back. And now I have two little equations to solve. And you can follow the solving steps here that are for fractional exponents. But let's see what happens if it looks something like this. Whoa, what? That's crazy, but do you see how there's something squared plus 3 times that something plus a constant? That's quadratic in form. So we're going to we have to write that word, we're going to let u be equal to x squared minus 5. Why x squared minus 5? Because that's what the middle term is, right here next to the number. Which means this can actually be written as u squared plus 3u minus 10 equal to 0. Which factors quickly to u and u. Factors of 10 that make 3. How about 2 and 5? Where 5 is bigger than 2. Now, once we've done our u substitution, we have to put back the regular function, which means we put back x squared minus 5 minus 2 and x squared minus 5 plus 5. We unsubstitute, essentially. Put back what we u substituted out. Well, this becomes x squared minus 7, and this becomes just plain x squared, because the 5s are going to cancel each other out. We set each piece equal to 0, and we solve. Add 7 to both sides, square root both sides. The square root of 0, still 0. So here are my 3 solutions to this crazy looking quadratic form polynomial. The last type of equation we're going to be solving today is equations involving absolute values. Now in Algebra 2, you did learn these steps, I think, but it was towards the very beginning of the year, so you might have forgotten. But it's the ISS. Isolate, separate, solve. What are we isolating? We are isolating the square roots. What are we separating? We're separating into two equations, one positive, one negative, and we're solving them separately. Isolate, separate, solve. It's very important we read this little exclamation point box. The absolute value of a number is never negative. Therefore, if U, which is the inside stuff, is an algebraic expression and C, the number it's equal to, is a negative number, then the absolute value of U equal to some negative number has no solution because absolute value would be positive. Let's see how this works. We isolate the absolute value bars. Are these absolute value bars isolated? Yes, they are the only term on its side. So we immediately go to the separate. And what I mean by separate is we're going to solve the regular equation, 2x minus 3 equal to 11. And we're also going to solve 2x minus 3 equal to negative 11. Isolate, separate. Now we solve. Add 3 to both sides. Divide by 2. There's one of my solutions. Add 3 to both sides. Divide by 2. Here's my other solution. Isolate, separate, solve. So what would isolation actually look like? I'm so glad you asked. Here's an expression that does not have the absolute value isolated, right? We minus 15 behind it and we multiply 5 in front of it. That's not isolated. It takes 2 steps to isolate this. So we have 5 absolute value of 5 absolute value of 1 minus 4x. We're going to add that 15 to both sides. We're then going to continue to try to isolate the absolute value bars by dividing by 5 on both sides. Once the absolute value bars are isolated, we separate 1 minus 4x equal to 3 and 1 minus 4x equal to negative 3. We solve. Move the 1 to the other side by subtracting. Divide by negative 4. That's 2 over negative 4, which gives me negative 1/2. There's my first solution. Negative 4x is equal to negative 4. X would be equal to positive 1. There's my second solution. Now I know that this video is a quick and crazy way of going over many types of equations. You had your polynomials, your radicals, your fractional exponents, the quadratic in form, and now absolute values. That's a lot of different types of equations that we just went over how to solve. Clearly, you can pause this video, you can go back to this video, you can play this video slower, you can play this video faster. Please make sure that you are practicing how you solve the different types of equations that we went over today.